And I think we can try to move on again to Dan Masters. Are you there? Can you hear us now? We see the, yeah, we are seeing your screen.
Sorry, I was just trying to find the unmute. Can you hear me?
Yeah, we can hear you. Okay.
Okay, great.
So yeah, so next speaker then is Dan Masters from Caltech. He will talk about from machine learning to human understanding. And thank you very much, Dan. Apologies for the technical issues. And I'll give you a warning 3 minutes before the end. Okay, thank you.
Okay, thank you. Yeah, and thanks to the organizers for giving me a chance to speak and for the great conference. And I was going to say, John, that was a great introduction to this talk. So thanks for that. Okay, so it's kind of a general talk, sort of advertising unsupervised learning and different visualization techniques. We've already seen a lot of that. So a lot of this might be a little bit repetitive, but I think it's still good to emphasize. So I think, I mean, the general idea of my talk is that like we really want to understand the data. And of course, with supervised learning, especially for things like classification, it's super powerful. But basically what we're doing is we're using training data where we've learned something about the data and we're applying that to new things where we don't have the extensive training data knowledge. So an example of that would be like getting spectroscopic redshifts for faint galaxies. It's very expensive and time consuming, and we can't do it for representative samples very easily. And if you want to do things like measure galaxy physical properties in detail, that's even harder. So unsupervised learning, John used these exact words in his talk, so I thought that was cool. Let the data tell us about itself. So I think the distribution of the data in the observable space that we have for the full sample tells us something important about the galaxy population. And so the question is, can we find the best ways to use that information? And we've already seen plots like these before. Yeah, in John's talk, he showed very nice TSNE maps, and that's what I'm showing on the left here from a paper I was on with a Caltech student, Beryl Hovlis-Offerblock. And on the right is a SOM built on basically Euclid-like data. So this is from a 2015 paper where we clustered galaxies according to their 7 or 8 colors that'll be measured by Euclid with the ground-based and space-based data. And so the key thing about these sort of techniques is that they preserve high dimensional relations in these low dimensions. So similar things group nearby, and you can see that in the galaxies highlighted on the sides of this SOM on the right, where I'm showing the SED represented by that cell, and then I'm showing 30 to 40 galaxies in Cosmos normalized to each other, and you can see that they're essentially identical within a cell. Okay, can't go to the next slide. Let's see, there we go. Okay, so an example of where a technique like this has been useful is redshift calibration via the SOM. So that map that I showed of how the Euclid photometry distributes onto a SOM takes advantage of the fact that you know in a large wide area survey, you see the same galaxy over and over. And so you can represent an entire survey like that with a finite, fairly small number of unique like weight vectors on a map like this, or neurons, whatever you want to call them. And so that approach, it was essentially a visualization of one type of clustering, but that led to a tractable approach to this problem of how do we calibrate photometric redshifts for weak lensing cosmology with these missions. And the reason for that is that we could actually, once we create the SOM, we can then put the spectroscopic redshifts we have onto that map. We can visually see where do we lack training data, and we can use that as the basis for targeting for a survey. And so that SOM-based strategy was the basis of, or is the basis of the complete calibration of the color redshift relation, or C3R2 survey, where we've gotten over 5,000 new faint galaxy redshifts in deep fields that have the required photometric data. Okay. And the SOM technique has also then been applied to existing weak lensing surveys or cosmological surveys, including DESI and QUIDS. So the plot on the left here just shows how you can use sort of an ensemble of SOMs, one that represents their wide field data, 4-band data in DESI, and one that represents their deep field data where they have better redshift constraints, and maps from one to the other to give you a good constraint on the redshift distribution of one of their wide field cells. And on the right here is a plot from Wright et al. 2020, just showing how SOM-based direct redshift calibration was working very well for the kids survey. And Angus will talk about that in more detail in a couple of days, so look for that talk. Okay, so enough about redshifts. What can we learn about galaxies? So Jari gave a great flash talk this morning hinting at this. I was just going to say a little bit more about it. So, so manifold learning like this, it represents the galaxies that exist in a survey and their relative frequency. And those photometric observables, when you have 7 or 8 bands of photometry, they're linked to the physics very tightly, not just the redshift, the physics of the galaxies. And you can see that here. The plot on top is from Jari's paper in 2020 using the Horizon AGN simulation. He built a SOM from the photometry from that data and then looks at the distribution of the galaxies that mapped each one of those cells. And spectrally, they're actually very, very similar. So not just in terms of photometry, but in terms of their detailed spectra, which is linked to the physics. And this is also borne out in a test case on the bottom from a paper by Shubi Hamadi in 2019. Just looking at spectra that come from a similar part of a SOM built on basically Euclid-like colors. And the spectra normalized to each other are remarkably similar if they're drawn from the same parts of that map. Okay, so then the question is, how do we extract the most information from these upcoming missions where we will have all sky data, but it'll be, you know, essentially a limited number of photometric bands. And so what Jari was able to show with that Horizon AGN simulation is that you can actually calibrate that map to measure star formation rate. But of course, to do that, you need training data. You need data that constrains the star formation rate in some way across the map. But if you have it, and it isn't too hard to get if you have a finite number of these regions to calibrate, then you can predict the star formation rate based on a galaxy's position on the SOM, go right from the observables to the star formation rate. And you get a much more accurate and unbiased estimate than you do with template fitting, where star formation rate is very difficult to measure. This is sort of work in progress. I just wanted to show it quickly, but something you can also do is you can cluster on a SOM that you've built or on a UMAP, which is shown on the right here. You can build bigger clusters of galaxies that share very similar properties in their observable space, and then look at their, for example, their spatial clustering and how it varies as a function of galaxy observables. And this could potentially be a very powerful way of looking at galaxy clustering as a probe of cosmology. And that's for, oh, I should have said that's work being done by Shubi Hamadi, also at Caltech. And this is also work in progress by Marzia Jafari-Azani, who's a postdoc at IPAC at Caltech, where we're looking at SOMs and then putting onto those SOMs very detailed physical measurements from surveys like Legacy, where you can really measure things like Lick indices of spectra, and seeing how they correlate with the inferred properties from template fitting. And of course, here we're dealing with the fact that these kind of samples are not fully representative, but it does hint at the fact that they do vary smoothly across this map. And if you could get a more representative sample, you could really go right to from the observables to these detailed properties. And then finally, I just wanted to say that I think, especially in the era we're about to be in, when we have catalogs with billions of sources from Euclid, Rubin, Roman, SphereX, these kind of surveys, these kind of visualizations are really powerful just for exploring the data and studying the data in detail, when the catalog itself is just far too large to deal with, and our brains just can't wrap around, hundreds of measurements, billions of sources, et cetera. So the example I'm showing here is just a SOM built on the same colors I talked about before. And you can see that there's a region of very red galaxies in the upper right, the U-G color shown on the left there. And then if you look at the median redshift of galaxies assigned to each of those cells, you can see there's a really clear boundary that happens very quickly up in the upper right. And we would assume that's probably the Balmer-Lyman degeneracy, but then what we can do then is just break out cells on either side of that boundary, which I'm showing in the plot on the right. And you can see that, yeah, indeed, both the galaxies that are found to be at lower redshift by the map have a strong red U-G color, but they have sort of a smoother gradient into the red part of the spectrum than the sharper break you see on the high Z part. And so you can really visually see how is this map distinguishing so well these things that have intrinsically very similar SEDs, one being high redshift and one low redshift.
3 minutes left.
Okay. Yes, I'm wrapping up actually. So to conclude, so I think unsupervised manifold learning visually captures like the key features of high dimensional astronomical data, and that really facilitates human understanding. I think something that really should be explored, that distribution encodes galaxies and their evolution. And these targeted training samples, if we can get them, they can really act as Rosetta Stones for interpreting the multiband photometry for millions or billions of galaxies from these surveys. And so that's a really powerful way, I think, of sort of melding like our human visual understanding, how we learn with machine learning. And that's it. Thank you.
Thank you, Dan. Do you have any question for Dan in the audience? Well, you think I have a quick one. So you mentioned that with the sum you can get more accurate SFR estimates than with template fitting. I guess it depends on the data, right? Because at some point, if you use, for example, spectroscopy, you can, using a template fitting on spectra, you can get quite accurate SFRs. So you think it's there's a sweet spot, or a moment where you get better, depending on the availability of data, you get better with template fitting, and when the data is quite sparse, it's better sum. And do you have an idea of where is this spot?
Well, when I was discussing that, and in Yari's paper, it's really about when you only have optical and near IR data, like we will with Euclid. And so there, we know because you don't have the far IR and you don't really have the UV, the star formation rate estimates are typically not that good from template fitting. But it turns out that those colors are constraining on the SFR at a level that we wouldn't be able to figure out with template fitting. They actually are constraining on the SFR. And so you have to discover that relationship with training samples. But yeah, I agree that if you have spectra, or if you have deep, FIR data or something like that, then that'll outperform. Okay,
thank you so much. We have another question on Slack by Bo Milvan Jensen. He's asking, can these manifold learning methods handle missing values and photometric uncertainties?
Yes. So with a SOM, so I was going to mention this. With a SOM, as John mentioned, you can build one SOM on a subset of your data, maybe deep field data, and then you can map new galaxies to it. And when you map new galaxies to it, you can take into account their photometric uncertainties. And so you can build up things like PDFs. And if you have missing bands, it's not a problem because you just don't use those in the association. I think with TSNE, John was saying that you can't do this as readily, but I think you can. It just takes an extra clustering step with TSNE, where you have to cluster things in your T-STEAM map, and then you can relate new galaxies back to it. But it's an extra step you would have to go through.
Okay. Thank you. Audience, no questions here. There's a last question on Slack before we move on by Gigi Guzzo. He's asking, how many training data did you use for the sums you showed at the end of the talk? And he's actually saying that is a question from a PhD student, Mariana Cagleri.
So from the last slide that I showed before my conclusion, that was built on, I think, about 200,000 galaxies drawn from Cosmos.
Okay. Thank you, Dan. Let's thank Dan again.